I'm Eglė Račkauskaitė, and I have experience from Imperial College London and Europe. Your program has said that I'm going to present about X1, and that was the work that I've done while I was at Imperial College London. But I hope to present to you something I think a bit more interesting, which is actually a continuation of the work which I've done at Imperial College London, but this is pretty much exactly the same experiment, but with a CLT slab slapped on top of it. So let's begin with the background. Mass timber construction. So most of us in this room are aware that there's a continuing and increasing demand by governments, developers, suppliers, architects to have mass timber buildings, which is mainly driven by the climate crisis. So we have a desire to reduce the embodied carbon in building and infrastructure. There's also building in timber also helps with the speed of construction. Sometimes it helps with the cost savings and obviously with architectural aspirations as it improves the feel in a space. And here on the right-hand side, you can just see a few examples published by the Council on Tall Buildings and Urban Habitat just this year on how mass timber buildings have helped in saving CO2 in a building in Origin, Quebec City. So there was 900,000 kilograms of CO2 saved, and similarly in a building which has recently been completed in London, Stadthouse, it took about 49 weeks to complete compared to 72 weeks it would have taken for an equivalent building. So timber is obviously an important aspect for sustainable construction. However, timber, unlike steel or concrete, burns and contributes to fire, so you have a continuous feedback loop between your structural material and fire dynamics in a room, which brings huge risks and challenges. So we have a challenge as fire engineers to evidence that the use of timber at scale can be safe in case you have a fire taking place. So we cannot take the risk which would result in the same conditions which we have for the purpose of sustainability when we have combustible panels on a building leading to huge fires. We need to take our time and make sure that the design that we are producing is not only sustainable but also safe. And here is just an example of one of the fires which happened at the University of Nottingham in 2013. So this is a building which was under construction, and obviously at the time it didn't have any complete fire safety precautions. It was naturally ventilated, and it has led to full building loss. So fire is not only concern after the building is complete, but also during the construction phase, because you have a lot of exposed timber with lots of natural ventilation. And usually the fire precaution measures, such as sprinklers or compartmentation or other protection materials, are not installed yet. So coming back to this challenge of making sure that timber buildings are safe, is in most of the countries of the world, we have a lot of regulations and design standards which fire engineers and architects follow to make sure that the buildings are safe. But these standards are designed for common building situations. And once you add timber, which is a combustible material, it's no longer a common building situation, and you have an increased risk in your building. Doesn't matter if it's low or high scale. And just recently, approved document B, which is a guidance document in the UK to help achieve regulations related to fire safety, has released a clarification on the applicability of the standards in the UK, saying that tall, large, or complex buildings where the structure is able to contribute as a source of fuel during a fire are not common building situations. And that means that the provisions and guidance which you have in your standard regulations and guidance documents are not enough. You need competent fire engineers and designers who understand the risks of timber in a building involved in a project as early as possible. So buildings such as this, one of the tallest buildings built in timber until recently is not a common building situation, and you need to provide additional provisions to achieve the same level of safety as for buildings built in concrete or steel. So nevertheless, there have been a lot of experiments carried out in the past decade, which have been tried to test compartments of buildings with combustible surfaces in various different configurations, and there's a lot of information that we have learned already. So if we take this figure as an example, so we have time on the x-axis and heat release rate on the y-axis, and this is a curve which should be familiar to most of the people in the fire industry. So if you have a typical fire in a compartment, you are likely to have a slow initial growth with flashover at some point, and then intense combustion until most of the fuel has burnt out, which then leads to decay. But once you add timber to the same compartment, some of the observations which we have from the tests today is that fire may keep on burning. That means that once all of the combustible fuel has burned from the compartment, there's still enough of exposed timber, which is a structure which is contributing and containing to sustain the burning within the compartment. So you are likely to have much longer fires than in traditional construction. Similarly, the fire may almost go out, but you might have delamination happening or char fall off, which exposes fresh wood, and that means you may have fire regrowing again and fire getting out of control, once again leading to increased fire duration and risk to the occupants and firefighters which have to deal with it. And these are just a few of the observations which we have today from experiments. And just looking at this, the behavior is very hard, if not impossible, to predict. Because even though we have a lot of testing, it's still not enough to say that this will be safe. And you have to take certain precautions when designing the buildings. Building on top of this, here you can see a figure which shows on the x-axis a compartment floor area against surface area to volume. So closer to the left is smaller rooms which are closer to boxes, like 10 meters squared, 100 meters squared, and further to the right is typical construction would be large open plan offices where you have lots of ventilation and space for the fire to spread around the compartment. So most of the experiments which have been carried out with timber construction today are very far on the left-hand side of this figure, with the biggest ones at the time that we did the experiments being approximately 90 meters squared. But the demand that we see for both non-combustible and timber buildings in Europe and worldwide is for much larger spaces. So open plan compartment floor areas up to 1,000, 5,000 meters squared, and there have been proposals in the US and UK for this type of buildings over the past 5-10 years. But we do not have experimental evidence to support our design methodologies, which would help with our understanding of fire dynamics in such spaces. This applies both to non-combustible and combustible buildings, but it's even more critical when CLT or timber is involved in a fire. So recently, a few years ago, we've published a letter to the editor in Fire Technology discussing these concerns, and this is mainly linked to large open plan spaces, so the right-hand side of the graph, where you are more likely to experience traveling fires, at least in non-combustible buildings. And traveling fires are fires which are likely to burn in a localized place and then spread around the compartment, either growing the size or just continuing to spread around. So when it comes to timber buildings, we have design methodologies developed on these tests, which are up to 84 meters squared compartments, but we need much more work and further validation for larger compartments. Yeah. As I said, oh, too quiet. Thank you. And there is a lack of experimental evidence for to develop design methodologies for larger mass timber buildings, so tall timber buildings or buildings with large open plan spaces. And this is the reason why at Arup we decided to invest in a series of large-scale CLT fire experiments to reduce that gap in knowledge and to build some better understanding to what we currently have. So Code Red is a series of experiments carried out in France. It was led by Arup with the support from a testing institute, CERIB, in France, where we built the structure, and some scientific research support from Imperial College London. And the main research aims of these experiments was to understand the effect of exposed timber on fire dynamics in large open plan compartments, decay behavior of exposed mass timber surfaces. So most of the experiments that are carried out for both non-combustible and combustible structures to date usually are terminated just once the combustible fuel in a room burns out. But we wanted to see what happens in the days after the experiment has finished, because timber has a tendency to smolder and combust for much longer. And we also want to compare the observed fire to the standard fire exposure to see how the fire spreads when it relates to the traveling fire behavior, and then charring rates of timber then compared against charring rates which are available in Eurocodes and design standards based on a standard fire exposure. We also had a series of experiments, so a second experiment in that series aimed to look at the effect of reduced ventilation on fire dynamics, and similarly we wanted to see the effect of encapsulation of timber on the fire dynamics and the effect it might have. So coming back to this graph, the largest experiment carried out today in terms of open plan compartment floor area was X1 and X2, so this is the experiment which is mentioned in a program which I led while I was at Imperial College London, and it had an open plan floor area of 380 meters squared. And this is the experiment which we chose as a basis for our experiments at Arup with CLT timber ceiling. So this experiment X1 has been carried out pretty much in the middle of nowhere in Poland in an old concrete farm building with the support of a lot of institutions, so Arup, Imperial, CERIB, EPSRC, ITB, and the main school of fire service from Poland. And here at the bottom you can just see a video from one of the experiments with the fire spreading from one side of the compartment to the other. So it had a fuel load of approximately 370 megajoules per meter squared, and the structure of this compartment was non-combustible. So when it comes to our experiments, which we did with Arup, we call them Code Red. The experiment layout of this building was identical, as close as possible with the limitations of construction to the one of a building in Poland. So we built a pretty much identical replica in France in a testing center. So it was about 10 meters wide, 34 meters long, and 3 meters high, with exactly the same locations of openings. It had a CLT 5-ply CLT ceiling with MUF adhesive. MUF adhesive is one of the adhesives which was found not to lead to char fall-off or delamination. We had 2 glue lamp columns in the compartment, 400 millimeters by 400 millimeters, and 1 steel column, protected steel column for comparison reasons on how the structure responds. The fuel was a wood crib, which was similar to the experiments in Poland, approximately 370 megajoules per meter squared, laid out across the whole compartment in a uniform manner. And we also had a bunch of instrumentation. So on the bottom, you can just see locations of lots of thermocouple trees. We had thermocouples within a CLT, glue lamp columns, steel column. We had 20 cameras, more than 20 cameras around the building, and then we also had 2 external screens to measure external flaming through the buildings, because we suspected that there could be an increased risk from that in terms of external fire spread. So the series in total consisted of 4 experiments, CodeRed 1 to CodeRed 4, and the main variables were ventilation and encapsulation. So CodeRed 1 experiment is an experiment identical to one of the experiments we did in Poland with non-combustible structure, with a CLT slab on top of it and 2 glue lamp columns, and which was a basis for the whole of the experiments in this series. CodeRed 2 is identical to CodeRed 1, with the only difference being the reduction in available ventilation from 21% to 10%. And we see that 10%, given the sustainability requirements for current buildings, is the more likely scenario if a fire were to occur. CodeRed 3 was slightly different and much smaller scale localized experiment to test a water mist system and how it would perform, because most of the current standard tests for water mist systems are with non-combustible sealing. So there's no knowledge how it would perform if there was a combustible sealing above the water mist system, and whether it would be able to control the fire and extinguish it. And CodeRed 4 was again similar to CodeRed 1, except that we had 50% of the timber sealing encapsulated just above the fuel bed. And so far, we have publications on 3 of these tests, with CodeRed 4 still analysis being done in progress. And in this presentation, I'll try to very briefly focus on the results that we have from CodeRed 1 and CodeRed 2, which already have published papers for them. So CodeRed 1, as I mentioned already, the aim of it was to study the impact of adding the CLT, and here you should see a video without a sound, which shows just a summary on what happened during the day of the experiment. So we did the experiment at night in spring, and the wood crib was ignited at one end in a linear manner and allowed to spread naturally to see what happens. And after a few minutes, when fire started touching the ceiling, we could observe large flame extensions across the ceiling, far ahead of the flames on the fuel bed on the floor, indicating very fast fire spread, which is, when it comes to design, is a huge risk to evacuation and to firefighters who have to deal with this fire. In total, the fire was about 22 minutes. And as I said before, we continued on observing the building a few days after the fire. And during the fire, there was no intervention from the firefighters. So going back to what happened during the experiment, so as I said, we ignited it at one end, and we had a line of methanol pans which were ignited simultaneously and allowed to grow, for the fire to grow. So here at the very top, you can see what it looked like 3 minutes after the experiment. So A indicates a view at the ignition location and from inside of the building, and B and C show the same view just outside of the building, with D showing what it looks like at the far end of the compartment. And the locations where you can see dimensions show external screens where we try to measure external flaming through the windows. And in the upcoming images, you can see how the fire developed in 40-second increments. So you can see here large flame extensions on the CLT ceiling, which were not observed when you did a similar experiment in a non-combustible structure in Poland. And it continued on growing quite rapidly after that. So I would like for you to pay the attention at the mark at 5 minutes, where you can see massive flame extensions almost all the way to the far end of the compartment, while the actual fire on the fuel is still pretty much localized at the ignition location, and then just in a matter of 30 to 40 seconds, the whole compartment is on fire. And when you compare this to the experiments that we did in Poland a couple of years ago, it indicates a significantly faster fire growth. So the blue lines on this graph indicate X1 and X2, the experiments carried out in Poland, and it shows the development of heat release rate with time, the estimated one. So it took about 10 to 15 minutes for a fire to grow to a significant size, while for the fire in Code Red, where the only difference was the addition of a CLT ceiling on the compartment, instead of 10 to 15 minutes, it took just 3 minutes for the fire to spread rapidly across the compartment and reach a significantly larger fire size, obviously, because timber itself is an additional source of fuel. And this is what it looked like just 6 minutes after the experiment, with massive external flaming through all of the openings, much larger than we observed in Poland. And these are photos of the building after the test the next morning. The charring at the top of the CLT is because of the external flaming, so there was radiation from the flames which were external from the ceiling. And then a couple of days later, we could observe some char through the CLT slab. And I'll discuss it in a bit more detail later. And the results, more detailed results from this experiment have been published in a paper in Fire and Materials. And if you want to learn more, feel free to get in touch with myself or any other co-authors to see nice figures and plots. And then the next experiment in this series was Code Red 2, which was identical to the one which I've shown you just now, but we had 50% less ventilation, so 50% of the openings around the building were closed for this experiment. And here is another similar video showing on what happened on a day during the experiment. So similarly, the wood crib was ignited at one end and then allowed to spread naturally across the compartment. And here we actually had some more cameras surviving compared to the first experiment, so we have a better view from what happened inside of a building. And one of the observations, which I'll show a bit later as well, was that we had massive external flaming. And this fire lasted for about 26 minutes. So it was a bit longer than the previous fire. And here we can see some smoldering and flaming a few days after the test has completed. Okay, so coming back to the ignition, here you can see what it looked like 4 minutes into the test when the flames just started impinging on the ceiling and the Again, similar large flame extensions across the CLT sleeving across the whole compartment, which were not the case in experiments with non-combustible structure. And similarly, once the flame started touching the ceiling, it grew in a matter of a few minutes to a full flashover involving a whole compartment in fire, and lasted approximately 26 minutes. So to compare this visually with some estimated heat release rates, this second experiment with reduced ventilation had a lower total heat release rate, but it lasted for longer because due to reduced ventilation, there was reduced available oxygen for the fuel to burn, so it took longer for the whole structure to burn out. And one of the main observations or conclusions from this test is that the extent of the external flaming. So it was slightly greater than compared to Code-Red 1, so the first test in the series, which is 3 to 3.5 meters in height. In Code-Red 1, it was 2.5 to 3 meters in height, which is bigger one we observed in non-combustible structure, and is a huge concern when it comes to fire spread to the floors above, and then also to the radiation, external fire spread to the buildings which might be adjacent to a timber structure. The fire was much smokier because we had less ventilation, so we had incomplete combustion, and for the same reason we had pulsating flames during the fire, and we also had very large lateral flame extensions horizontally away from a building, which you can see in an image in the top right. And similarly to Code-Red 1, Code-Red 2 results have already been published. And if you want to learn a bit more and see at the actual results at the thermocouple data, feel free to get in touch with me or get a copy online. So one of the topics that I would like to touch, and which is not usually that is something addressed by the design standards or the designers, is the concerns related to smoldering. So timber is a combustible material and can have a tendency to burn in a way that you cannot see, which is smoldering is a flameless combustion and can usually be invisible to the naked eye. So here in this picture, you can see what the CLT slab looked like 3 hours after experiment in visual, but once you look at it through the infrared, you can see a hot spot forming across one of the beams in the compartment. And as the time went on, this hotspot grew over the upcoming days and led to burn through the CLT slab. And after this experiment, we observed hotspots in at least 3 more locations with burn through the CLT slab, which is concerning when it comes to, especially to firefighting operations. Also, not to mention that here we were able to observe it with infrared cameras, but it might not always be the case because infrared cameras might not always be able to observe these hotspots if there are some obstructions in place. So they might not be as easy to detect as well after a fire in a real building. So there's a real concern in terms of stability of the structure after the fire and safety of it. And similarly to this one, after Code-Red 2, we also observed a lot of hotspots. So the figure on the left part is a view from the top into the compartment, and everything is orange, indicating that the CLT ceiling is still hot as the fire has just ended, but 12 hours in, and you can already see a formation of a number of hotspots in the compartment, which then grew with time, resulting into the hole in a CLT slab. And in this experiment, As I mentioned, we also had two glue lamp columns in the compartment, and in this experiment, we had one of these columns collapse because the base of the column has burned through long after the fire. So we found it collapsed in the morning next day after the experiment. So not even immediately after. And also to bear in mind that these columns were unloaded, so most likely would have collapsed much earlier if we had an actual loading on top of it. So some of the key observations from these experiments, obviously we don't cover everything. We suggest some of the first ones. You can find many more in the papers which we have published, but the biggest concerns is that fire spread across large areas of exposed timber is fast and much faster than if you had the same structure without a CLT slab, if it was just a concrete or steel structure. And this is an issue which not many people have considered to actually be an issue before, and is important when it comes to evacuation, because that means the amount of time available is significantly reduced. Also, the external flaming and the likelihood that the fire will occur for 2 floors above the fire floor is also significantly increased when it comes to comparing that to a non-combustible structure, just based on the extent and observations of the external flames. We also had some internal work done where we tried to make comparisons with existing design methodologies for external flaming, and we are nowhere even close to addressing this risk. So there's a lot more work needed on this, and it's a big issue. Then what we have observed is that the lower portion of exposed CLT columns may be very vulnerable to combustion and smoldering, because you usually have fuel on the floor or any other location where you have fuel, and it might smolder for long durations, even after the fire, leading to invisible burn through long after, which might lead to unstable structure. This also applies to, you would also expect this in where you had vertical walls and similar arrangements. Then another important factor is smoldering. It will occur in a CLT slab and will be invisible even in some locations, even with infrared cameras. So there's a real concern on how to identify them for the fighters to extinguish them. The positive thing is that in experiments that we did, we tried to extinguish some localized hotspots, and we were able to do that. So it's possible to extinguish them. The biggest issue is identifying them after the fire and the risk of safety to the firefighters and trying to access them. And also the fact that we don't currently have compartment fire models which would be able to accurately reflect the fire dynamics which we have observed and would enable us to design safer for timber structures. So there's still a lot more work and research which needs to be done on this topic. So that's all I had for you today. Thank you. And if you have any questions, feel free to get in touch with me or any of your collaborators or ARP to learn more about these experiments. Thank you.
Eglė, would it be a true lie or a bad lie to say that so ecological construction as wooden is not sustainable, actually? Well, after the fire, we have to remove it, or can we repair it?
You have to look, I guess you have to look at the cost, because sometimes it might end up still being cheaper. So there's still a lot of research which needs to be done on what repairs might be required, and that comes to the structural stability when it comes to smoldering, identifying what needs to be repaired, because it might be easier and quicker to repair this timber because it's faster to construct, so it might also be faster to repair.
Okay, thank you very much. I'm very happy we have started discussion about wooden constructions, and we have such a big experience just next to Lithuania in Poland.